She is currently a cryptography researcher at NYU Shanghai. She has completed her PhD from University of Chicago in 2022, recently only. So her research primarily focuses on studying the security of cryptographic primitives. More precisely, her work focuses on understanding the role of memory in the security of cryptographic primitives. So thank you, Dr. Akshima, for accepting our invitation and visiting us. Over to you.
Thank you so much for the introduction. And studied in terms of cryptanalysis in cryptography. But in terms of this problem, like collision finding, which is a very relevant problem in cryptography, they have not been as rigorously studied, and there are like people have started studying them fairly recently. And I'll be talking about most of the work covering this area. So there are like a handful of papers that have studied this problem. So this is the outline of the talk. I will be talking about the basic definitions. Then I'll present the model. I will be precisely defining the model for collision finding with pre-computation. Then I'll give a comparison of the results. And then I will briefly, on a very high level, talk about the techniques and how they are different in the how different results were obtained from these different techniques before I conclude the talk. So please feel free to interrupt me and ask questions because it might affect if you don't understand one thing, it might affect the understanding of the following concepts. So feel free to interrupt me. So starting with basic definitions. Cryptographic hash functions are essentially functions that map arbitrary length string to output strings of fixed size. So so basically they map a larger domain, and it could be possibly infinite, and map it to a fixed size domain. They are widely used. Especially in cryptography, they are widely used. You can think of a lot of applications such as digital signatures. You can think of pseudo-random number generators. They are widely used, and when they're used in any application, in order to talk about the security of the application, you might need more properties from these hash functions. So one of the most popular properties that is required is collision resistance. So of course, when these functions map larger domains to smaller domains, there would exist two strings that would map to the same output. So obviously the collisions exist. What we want in the collision resistance property is it should be computationally hard to find these collisions. So say if you have an output domain of size 2 to the 512, we would want that finding collisions require something order of 2 to the 256 time. So why these collisions can be damaging in practice? Think of digital signatures where generally the constructions are such that you sign the hash of the messages. Say you have two messages and you have hash of a message, and that is what it is signed. So if there are collisions in messages, if it's easier to find collision in messages, it's easier to forge the signatures. If anybody is aware of digital signatures, if not, then it's fine. Just these can be damaging in practice. That's all is the thing that I want to point out here. So generally, when we study the security of an application, we first have an adversary. So adversary is any malicious algorithm that is trying to prevent the application from achieving its security. Whatever security we want from that application, the adversary tries to prevent the application from achieving it. So we model the adversary as it gets to make a bounded number of queries to the application. Here it's the function h, and it's thought of as computationally unbounded, and hence you can think of as deterministic. Okay, and so if you don't put any restriction on the hash function, you can't say anything about how hard it is to find collisions on the function, because this is like a P versus NP problem. So generally, we think that this hash function is a random function. and then we study the properties of the application. So this is the random oracle model, where we pretend that H is a random function, and then we give proofs, and we study the security. Why is that? Because for a random function, you can
I think slides are not shared.
okay, no. Sorry about that.
Thanks.
Where is my video? Oh, yeah, it worked. So sorry about the slides. Why we study random functions particularly? For random functions, we can give an unconditional proof that finding a collision requires order of square root n time. If this random function has output domain of size n, then square root n time is required. Generally, order of square root n time is required. And this, so the probability of finding a collision is t square over n. If an adversary is making t queries, the advantage or the probability of success is t square over n. And this comes from the birthday attack. Are you aware of birthday attack? Okay, cool. So think of a random function. So basically think of the set of all functions that have this input domain and output domain. And you pick uniformly one function that is a random function. Yeah, you can. So basically, yes, I'm modeling. So I am modeling the hash function as a random function. Does that answer your question? Okay. So that actually leads me to the next part. Right now here, I'm thinking of the hash function as a random function. But when we construct these hash functions, we don't know how to come up with functions that take arbitrary sized input and output a fixed output length. So how we generally, like in practice, we use constructions like, okay, I can no longer move to the next slide. Okay. So one of the most popular constructions is Merkle-Damgard construction. Here you use a compression function. So compression function is essentially anything that has a smaller output domain than the input domain. And so here we have a compression function little h, and this construction takes any arbitrary length input, say x. Here in this example it's x. It breaks x into fixed size blocks, and each of these blocks belong to M. And then it iteratively applies the compression function. So this is the construction. And so from here on, we'll talk about all constructions where this little h, the domain would be from n times M to N. And so if you think about the best attack on this, now how you would model the attacker would be, attacker now gets to make t queries to the compression function, and it is required to find collision in the Merkle-Damgard construction. So it's making queries to little h, and it has to find two distinct strings that have the same output under MDH. Yes, same hash output from this Merkle-Damgard construction. This is just a construction. So if you think about that, there was no, you did not know the construction. It was just like an oracle for you. And now you know the construction, like how that hash function was built. So here the adversary has more knowledge compared to a random oracle, like where initially our h was just a random function. Now our MDH is not a random function. Little h is a random function. Now we'll think of the little edge compression function as a random function. Okay?
Both SHA-1 and SHA-2 are actually this.
Okay. Can be different from our SHA methods.
This is an abstraction of that kind of construction.
SHA-1 and SHA-2 are not exactly this.
Okay.
So SHA-1 and SHA-2 are based on this construction. Okay. Sorry, I didn't get your question then. Now the adversary has more knowledge about the construction and it's still making t-queries. But despite having more knowledge, the probability that the adversary can find a collision is still t square over n. So throughout the presentation, we'll be talking about adversaries that make t-queries, and the probability of finding collision is still t square over n. So the best you can do is still abort the attack. But this is when adversary does not know anything about the compression function beforehand. So everything that the adversary learns about the compression function is from making those t-queries. We can think of adversaries that take the compression function, do some computation, store some information, and then do this attack. Such attacks actually exist. So if you think about rainbow tables, I'm not sure if all of you are aware of it, but like think of the lookup tables. All of these, what they do is they do the computation, they store some advice, and then they use that advice to do better attacks. So these such attacks, they work in two phases. In the online phase, the objective is to do a better attack compared to when you did not have the information, and maybe get like better amortized time or something like that overall as well. So, and it's important to study pre-computing adversaries, first of all, because they also capture non-uniform adversaries. So, and it's important to study non-uniform adversaries, especially if you're studying composition systems that have compositions. So they are composed of different components, and you want to study the security of the entire system. Sometimes you need to study the non-uniform security of the components. And apart from that, these also capture very strong adversaries like who can do these kind of computations, crazy computations, because they have those resources. So next, I'll precisely define our model for collision finding with pre-computation. So this was first given by Unruh in 2007. In this, the adversary is a two-stage algorithm. In the first stage, the adversary gets unbounded access to the hash function. Let's go back to now only hash functions. We are in that model, and the adversary gets access to this hash function. Think of this hash function as a random function, and it computes something on it. It outputs an S-bit advice, so it gets to only output a limited size advice. And then it gives that to the online stage adversary, the second stage of the algorithm. And that algorithm now makes queries to this hash function. Again, it gets to make t queries, and it is required to output collisions. So for such an adversary, what do you think? What could be the success probability of such an adversary? I would say it's constant, because I could just pre-compute a collision. I can store it in my advice, and I'll just output that. So no limit on the pre-computation? No, there's no limit on the pre-computation. It's unbounded. The only limit is that you don't get to output too much. You can output S-bit, bounded size of advice. So there is no computation limit or no limit on the number of queries you make in the offline phase. In the online phase, there is a limit on the number of queries you can make. So for such an adversary, it's trivial. Finding a collision is trivial. So Dodis, Go, and Katz in their 2017 paper said for pre-computation, it's meaningful to study the collision problem only if we look at sorted hash functions. And sorted hash functions, you can think of, this is a way of domain extension. And also you can think of them as instead of attacking a function, now you're attacking a family of functions. So this is basically, this just does domain extension. So your advice remains the same. You're extending the domain, and now this should make finding collisions even with pre-computation hardware. So now what happens is, again, the adversary in the offline phase gets access to the function. It outputs S-bit advice. Then in the online phase, it gets one particular salt, and it has to attack that salt. And it has to find collisions such that, so it gets A, and it gets to make T queries, and it has to output distinct X and X prime, such that H of AX equals to H of AX prime. And for this, they showed that the success probability is S plus T square over N. It's for sorted, yes. So the longer the length of the salt, bigger would be, like, basically N is the salt space. What would be the? Yeah, your M could be equal to N. So if that happens, then you don't really need hash functions. You can work with compression functions, or you can work with something, you can build something smaller. The point of having hash functions is you have a huge input and you want to make it something smaller and something you can work with. So, I mean, it is possible, you can do that, but it just makes more sense if your input length is insanely huge or something. So they showed that this is the advantage. If you compare this to what we had in when there was no pre-computation, then the advantage was T square over N. So compared to that, you are not losing that much. So even with pre-computation, especially if your S is smaller than T square, then pre-computation should not really help, or they shouldn't matter. And so this is for a hash function. Now this becomes the optimal security. And now we want to test, how does Merkle-Damgard stand to this test? So for Merkle-Damgard, now what will happen is, in the online phase, you get unbounded access to the compression function, and you output again S-bit advice. In the online phase, you get the sort. You get to make T queries to the compression function, and then you have to output two distinct strings that would collide under the Merkle-Damgard hash function. And Coretti et al. Were the first one to study this, and they found an attack that could beat S plus T square over N. And I want to present that attack next. It's a beautiful attack. So how their attack works is, in the offline phase, they start with the offline phase, they pick S solves, and on those S solves, they iteratively apply the compression function with zero message. And after doing this T over 2 times, they would obtain another set of S solves, right? And for this set, say the set is now A1 prime, A2 prime, and so forth up to AS prime. And for these solves, what they do is they find one block collisions. They find X and X prime such that H of AX equals to H of AX prime. This is what they do. And then in the advice, as advice, they store this AI prime, XI, and XI prime. So basically, they're storing order of S collisions, one block collisions in their advice. So if you make a note of how many nodes are there on these trails, so there are order of ST nodes on this trail. Then in the online phase, the adversary gets the sort, the challenge sort A. On that, it iteratively applies the H, the compression function, with zero message. And it does that up to T times. If in the first T over 2 times, if it hits any of these nodes that we had in the pre-computed trails, then you know you would win, right? You would reach one of these AI primes, and you can output a collision. Right?
So in the starting value and the point where the collision happens.
No, we don't even need to store the starting point. We just store the endpoints and the collision on that point.
Achieve that point in.
You want to achieve at least one of the points on the trail in T/2 computations, so that in the rest of the T/2 computations, you can reach one of these AIs. Yeah. So now the probability that such an adversary wins is ST square over N. So yeah, so because here you have order of ST size trails, nodes on this trail, and if you hit any one of them in the first T/2, yeah, so you get ST square over N. And the thing is, the beautiful thing about this is the adversary does not have to know in the online phase that one of these nodes are on the trail or not. It just would eventually find out if it's on the right trail. Any questions about this attack? So they're kind of using the idea that the adversary in the offline phase saw this node, and it does not know if it saw the node, it has seen the node or not until it reaches one of these AI points. Once it reaches one of those AI points, it will know, okay, I had hit something right and I win, that's why. So here, if you see, the advantage is ST square over N instead of S plus T square over N. So this suggests that Merkle-Damgard is not a good construction, because with pre-computation, it can no longer achieve the optimal security. But there is one thing to note here. The collisions that you're finding here, they can be T blocks long, because you're computing order of T times, and you're hoping in also on average in order of T time you would hit, like these trails that you will get would be order of T long. And if you try to put this in perspective, so consider SHA-2, where n equals to 2 to the 256 and m equals to 2 to the 512. Say your advice is 2 to the 70 bits long. Then this attack suggests that you would need, you need to make 2 to the 93 queries in order to get constant advantage. But also you would get collisions that could be 2 to the 93 blocks long. And 2 to the 93 block long collisions are basically yottabyte long collisions. This makes no sense. Finding such collisions in applications make no sense. So even if you are getting such an attack in Merkle-Damgard, practically it could be irrelevant. So say if you want to restrict that in my application, I allow only collisions that are b equals to 2 to the 20 blocks long. Then the best attack we could find, so in the first prior paper, the best attack we could find required 2 to the 166 computations or queries. It required that many number of queries. So compare that to 2 to the 93. Merkle-Damgard, like their attack is way too pessimistic. And the best attack we could find, the advantage is STB over N instead of ST square over N. So maybe you can still save the Merkle-Damgard construction if you can ensure that SB is not big enough. So this was our paper this was a paper with my advisor David, Andy and Hotek that in 2020 paper, where for any B block collision finding, we conjectured that this STB over N attack is the best attack possible. And so we tried to show that, but we couldn't show that. We could show it only for a restricted class of pre-computing adversaries. We couldn't show it for any adversary. So why we still believed in this conjecture was because for 2 block collisions, we could show that the this is the best attack, and the best advantage is st over n plus t square over n. So this suggests, so in order to defeat the optimal security, or for Merkle-Damgard to be really bad, S has to be greater than T. So there was a follow-up work by Ghoshal and Ilan, and they were able to prove our conjecture for constant P. And how they did that was they got a bound that was exponentially large in B. So whenever B is a constant, we would still end up with st over n bound, st plus t square over n bound. But as soon as B becomes any larger, this bound becomes meaningless. So they gave another bound, S4TB square over n, which was general and it would work for any B. But whenever S cube B square is greater than T, in that case, this bound is even worse than ST square over n bound. So this told us nothing, whether like, so it just told us for B equals to 2, maybe the attack that so whatever bound that Kuretti et al. Gave was very pessimistic, and maybe Merkle-Damgard is not that bad. And then in our 2022 paper so this is my paper with Xiao Guo and Jipong Liu. In this we gave another bound. We gave a bound of max of 1 st and st square over n times stb over n. So I know it's a very crazy bound. So let me just walk you through what this bound means. So the case one is st square over n is less than or equal to 1, in which case our bound is stb over n. So we proved the conjecture there. The conjecture from the ACGW 20 paper, we proved that here. The other case is when st square over n is greater than 1. In that case, our bound is stb over n times st square over n. So even though we don't know if the conjecture is true or not, we still know that Merkle-Damgard is not as bad as st square over n. We can still, it is still like linearly bad as your length grows. As if your applications allow longer and longer lengths, worse and worse is the security guarantee of Merkle-Damgard. So this confirms that bounded length collision finding is harder, and this was our result. So finally, I want to compare the techniques of all these works, because I think we found a connection which is very interesting. So in the Kuretti et al. Work, how they found their result, how they gave the result was they reduced to a bit fixing model. So now if you think of the pre-computation model, the problem is you think of the compression function as a random function, but you allow the adversary to pre-compute and get some advice. So now this random function, you can no longer think of as this compression function as a random function, because there is some information on it. So whatever your H is somehow has to be concurrent with your advice. So you can no longer think of it as a random function, and that is why it's very hard to analyze pre-computing adversaries. That's why Kuretti et al. They reduced it to a bit fixing model. So what is this bit fixing model? In this, the adversary gets to, so again, the adversary is a two-stage adversary. In the offline stage, the adversary fixes P points in this compression function. And then in the online phase, the compression function is concurrent with these P points. So these P points remain the same, and the other points are random. And the adversary is required to, within T queries, it is required to find the collision on the challenge salt. This is the bit fixing model. So there is no advice, nothing. Just in the function, in the compression function, your P points are fixed and the other points are random. So, you had a question? So, and they showed that if P equals to ST, and bit fixing model, the advantage in the bit fixing model when the adversary makes T queries is delta, then the advantage in the pre-computation model, where the adversary has S-bit advice and T-queries, the advantage is order of delta. So what they did was they gave this reduction, and then they showed that in the bit fixing model, the advantage is order of st square over n, and this implied an advantage of order of st square over n in the pre-computation model. But in our 2020 paper, we realized that bit fixing model can no longer be used to get any better bounds. So we got a better bound, we got st over n, but we realized this bit fixing model cannot be used. We showed that. So we reduced to another model, and this is the multi-instance model. A variation of this model was first given by Impagliazzo and cabinets in 2010. And so this model is now you're not getting any advice or anything. You get to instead of solving one instance, you're required to solve S instances. So you get S solves, you get one solved, you get to make T queries, and you have to output a collision. Then you get another solved, and so on and so forth, you get S instances. And now in order to win, you have to win on all the S instances. So this is the model. And now we can show that if the advantage in this multi-instance model is something delta to the S, where S is the number of instances, then in the pre-computation model, the advantage is 2 times delta. So what we did was we just showed that in multi-instance model, finding 2 block collisions, the advantage is as most st plus t square over n to the power s. And this implied that the advantage of finding 2 block collisions in pre-computation model is st plus t square over n. And the follow-up work of Ghoshal et al., they also used the same model. They just fine-tuned how they got this, they just fine-tuned how the multi-instance model result was proved. So in our 2022 paper, we again reduced to this multi-instance model, but the way we viewed the multi-instance framework was a little different. So in the 2020 paper, so say xi is the indicator that you succeed on the ith instance. So in this, how we were analyzing it was, we were analyzing the probability of simultaneously winning on all the S instances. What we did in the 2022 work, we instead started analyzing the probability of winning on the ith instance, given you won on all the previous I-1 instances. So what that meant was we just needed to bound this probability of xi equals to 1 given x1 through xi-1 equals to 1 to delta. So if we could show that this is delta, then we can show that the probability of winning in pre-computation game is delta. So if you compare this bit fixing and multi-instance model, you would realize they are very similar. Like in the bit fixing model, the adversary gets, in the offline stage, the adversary gets to fix st points. And then it gets the challenge solved, and then it gets to make T queries, and it has to win. In the multi-instance model, the adversary, if you are analyzing the ith instance, the probability of winning on the ith
back at 4:30. 10:30 to 4:30 would be wrong. So we check the brother. While the electricity comes, why can't we analyze this for bond construction?
Yeah, we can do that. That's what we're doing next. So there are some preliminary results, but Sponge has its own issues because it has permutations. So there are inverse queries that are possible. So analysis becomes more difficult.
But you're not allowed the entire full inverse. Are you assuming both pi and pi inverse?
Yeah. We are reverse. If we assume that there are no pi inverses, then it's essentially Merkle-Damgard. Sponge becomes interesting when we allow the inverse queries. And in fact, we for at least for some B's, particular B's, we know that it could be worse. Sponge, the security of Sponge in pre-computation model could be worse than the guarantees of Merkle-Damgard.
And one thing is, in short of 56, I think the message size is limited to 2 to the power 64. Not sure, but I think. Because if you look at the last block padding, if I remember correctly, 64 bits are left for the message length. Is that right?
That could be there, and that is fine if we are doing padding here. Because if you think of the attack, we are actually finding collisions that are of equal length. So the padding would also be equal.
No. The length of the padding cannot be more, the length of the message cannot be more than 264.
Okay.
So in your previous slides, in the initial set of slides, you were showing long block messages.
Yeah.
That will be invalid by default.
By default, okay.
At least on this specific construction.
Okay.
So if I remember correctly, it is 64.
Okay. Yeah, so it becomes even more relevant to study bounded length collisions.
That's what I'm just check it. If I remember correctly, it is actually that.
Okay.
Like it is just like earlier, so they okay.
Switch off.
Problems of being too smart and smart classrooms. What's the job? Okay.
We were looking at the similarities. So basically in the bit fixing, the adversary fixes ST points. And in the multi-instance model, when we are analyzing the ith instance, there are at most I-1 times T previous queries, which is at most ST queries. And again, after that, the adversary gets the ith challenge. It gets to make T queries and it has to win on the ith challenge. So these are very similar. In fact, like if you show that the success probability is delta in the bit fixing model, it implies order of delta advantage in the pre-computation. And similarly, if you show that the probability of winning on the ith instance, given you run on all the previous instances is delta, then in the pre-computation model, it's 2 times delta. So we realized actually this multi-instance model is a generalization of this bit fixing model. Because what is happening in the bit fixing model is basically it's a, okay. So basically this bit fixing is a worst case analysis. And in the multi-instance model, we can analyze the probability that the bad things happen or like the good things for the adversary happen, and we can get better results. So because we were able to do an average case analysis in the multi-instance model, we were able to get better results.
Reduction from 2018 paper or something. How you select the paper for the reduction is related to the your one. How you identify?
How we identify like how this model could be helpful. So the thing is, for us, at least for the Impaliazo and cabinet result, they had used this model for solving this pre-computation for some other problem. So for us, it was easy.
Something different, or their computation is something different.
Yeah, they were solving a different problem, but the thing was they were solving it with pre-computation. So we thought, okay, with pre-computation, it means somewhere when you have S-bit advice, that sort of points to ST points like you're sort of fixing ST points, because bit fixing, that's what's happening. Your S bit advice sort of like, so the thing is, in the ideal case, if we are considering an adversary, that its advice is basically just S points. It's just recovering S points in the compression function, and it's storing that as advice. But a smart adversary could do something more. It could save a function of this. So we sort of like this bit fixing model. This was actually first used by Mike Goose in one of his works, where he was doing communication complexity analysis.
For the reduction, their idea or their whatever the definition.
So yeah. They're using these models again to like solve a difficult problem, because even in communication complexity this happens, right? If I am allowing a limited communication, I am somehow saying, okay, so adversary could again compute some function on its previous stream or on its input, and we somehow still want to say that this S bit cannot give you too much information.
Multiple assumptions when you define anything, some specific additional parameter or additional thing. Because in your case, it improved from previous one to the your one, then again you modify it and finally come up with some solution. So these assumptions are mandatory, or somehow without assumption also there is a possibility to solve similar type of problem with same complexity.
So here, I think the biggest assumption that we have is that the compression function is a random function. We tried to do away with that, and we tried to think of an arbitrary function, and we couldn't prove anything, but we have this intuition that for any arbitrary function, it should only be easier to find collisions. Like random functions should be the hardest to find collisions. So like this assumption is there. I mean, this assumption is important in a way if you want to say something, like unless you have to place some restriction on the compression function. If you... Yeah. The thing is, again, that again points to a P versus NP problem, because if you're given a collision, you can easily verify it's a collision or not. Say you're given two distinct, you can easily verify, but finding a collision, is it as easy as verifying or not, then it's again like P versus NP problem. So in order to not go into that issue, we have to have some restriction on the function.
One of the so all of these cases, how you validate the ideal one? Mathematically, how you validate? Whatever you define that this is the complexity from the reduction or whatever complexity to bit fixing or whatever. So then how you prove it, validate it?
So there are like two different, like these are two different areas. So especially for this area, time-space trade-offs, generally we reduce to a problem in communication complexity, because that is generally, you look for some models there and you look for something there, because communication complexity, they are doing essentially something similar here. Like they're restricting the communication, but you can also think of that communication as memory. So you're restricting the memory that you're sending from one stage to another. So generally for this time space, so generally we look for results there. For the other paper, which was on searchable encryption, there we reduced the problem to an algebraic problem. And then we worked really hard to solve that algebraic problem. So there, like you generally have to come up with, you have to basically think of the easiest thing, like you have to think of the problem in the easiest form. You have to model it in such a way that you can do something about it, you can say something about it.
Solving the validate the ideal one. So those are the your one, or it is
So the lemmas and theorems are ours. I think one theorem would be So we have used compression-based proofs. So one of the only theorem that we've used from prior work would be which says that when you're storing a random function, so any storing like a random string from say size m-sized space, you require log m bits. So that is one result that we've used. So yeah, that was generally like the conclusion and everything. And I just want to talk about some of the open problems. So for Merkle-Damgard hashing, we still have a little gap when st square is greater than n. So maybe solving that is one of the open problems. And another one, as Samata sir said, for sponge hashing, we have some preliminary results, but there is a huge gap between the lower and the upper bounds. And another area where we can think of time-space trade-offs for collision finding is in the quantum setting. So quantum setting is a giant in itself that we need to think about, because if we want to come up with good post-quantum hashing algorithms, we need to analyze in the quantum setting. And in the quantum setting, then you can think about, okay, we have a classical advice or we have quantum advice, and quantum setting has its own issues. And somehow we want to show that the only gain that you can get in quantum setting is from Grover search kind of search algorithm. That is somehow, that's what you want to show. So yeah, that's another, which is a very interesting thing.
Kaimin too had a paper with advice on pre-image for any function cap. So I'm actually working right now on this third one about this collision and this.
Yeah, we are also thinking about this in the with the collision finding, because pre-image is still there is a paper on that, but collision finding, we are not even able to show anything for b equals to 1. So one block collisions, also we can't like.
Yes, we could only do global.
Yeah. So the best attack is still like the advantage comes from the global search. Yeah. So yeah, that's all. Yeah.
Something like access pattern kind of.
Access pattern kind of.
Means like you are reducing the communication cost on the basis of this type of form. So if there are 2 points communicating between access pattern, like this person communicating with that person, whatever the message is encrypted over somewhere or in some form. So
The advice is not encrypted. Advice is because it's the same algorithm, that is stage 1 and stage 2 of the same adversary. It's not encrypted, so we don't have to worry about the access pattern. We know what's the advice. The only thing is, so basically you can think of, when you say S-bit advice, you can think that I can see the entire function table, but I can't store the entire function table. I can store but only S bits of that entire function table. That's what's happening here. There is no issue with whether the advice is encrypted or not. It's not encrypted. You're just sending the advice. It's just 2 parts of me. So when we talk about 2-stage adversary, it's just 2 parts of me. Like one part sees something but can't remember too much of it. And second time, when I'm attacking it, I can only see some limited information. And then I have to attack. Thank you. Thank you so much.